we did last time. I covered a bunch of different topics, and so I want to just go back and try and get the essence of it before we go on. What we're going to be talking about from last lecture to next lecture is the perceptual analysis of image shading. And so the idea is when you look at these figures up here, you see different shapes that are specified to you by the shading, or chiaroscuro as it's referred to in the art world. You can also sense different material properties, and somehow we're able to get both of those things from the pattern of shading, and also know something about the pattern of illumination, which we'll talk about next time. Now, the key thing to understand why this is a difficult problem is that there are three different things that affect the shading in an image. There's the 3D structure of the observed scene or object. There are the surface materials in that scene, so the difference between glass or metal or plastic. And also the overall structure of the light field can also affect what we see. We'll talk more about that later today. So one of the things we're going to worry about is how is it that we have a single pattern of shading and we're somehow able to tease apart all these different things that are adding together to produce that pattern. Now, here is an example of how this works in art. This is Vermeer, Girl with the Pearl Earring. And what we're going to try and understand for this lecture and next is why is it that this works as well as it does in order to specify the 3D environment. Now, there's one other thing I want to highlight from the last lecture, and that is this idea here, which is that the illumination varies with the angle of incidence of the light beam. So the idea is that, let's say I shine a light directly perpendicular to a surface, that light beam is going to be focused on a smaller area than if the light hits the surface at a glancing blow. And that's what's described here. So in this case, the light beam is going to form a circle. In this case, the light beam is going to form an elongated ellipse. Now, the key thing to keep in mind here is that illumination is the amount of light falling on a surface per unit area. So if the same amount of light for a light beam is spread over a large area, you have less illumination than if that amount of light is spread over a small area. Any questions on that before I go on? You can see that here. That's why. Oh, this is annoying. These batteries go out so fast. Anybody have a spare set of batteries on them? Looks like AAA. All right, I'll have to do it the old-fashioned way with my hand. What's that? And I don't know why the slide progression works, but not the laser pointer, but apparently it does. I guess the laser pointer takes more energy. So the key thing to note up here is that depending on the orientation of these faces, they can be brighter or darker depending upon their angle relative to the illumination. Now, the other two things I pointed out last time I want to highlight again is the distinction between lightness, which is the perceived reflectance of a surface. So if I perceive your jacket is black and his shirt is white, that distinction is what we call lightness. As opposed to if I'm trying to distinguish the amount of light that I'm seeing in one region or a different region, that's referred to as brightness. So we'll spend a lot of today talking about lightness perception. Now, the classic theory of lightness is that we use the ratios of different regions, and the basic idea proposed long time ago was that lateral inhibition, what it does is it gives us a ratio of the amount of light in one region relative to neighboring regions. And that was purported for a very long time as explanation of how we solve light in a perception. So the basic idea is if you change the level of light, right? So if you have a black shirt and you have a lighter shirt, the ratio of the luminance in your two pieces of clothing is going to stay the same, even if I make the lights brighter or I make the lights dimmer, right? The relative luminance between different surface patches will be the same. Now, the key thing, there's a real important assumption that makes that work, and that is they'll both be illuminated in the same way. So if that's true, then the idea is you can use luminance ratios to judge lightness. Now, fairly early on, it was determined that that can't be the whole story. So this is one of my favorite examples of that I showed you last time, where you see this as a homogeneous gray ring, but if I pull them apart, the one on the right side gets darker. Here's another example where if I slide it down, then you get this weird transparency effect. And so the question is, by the end of the day, I'm going to try and explain to you why this happens. Here's another example, the White's illusion, which I'll also explain to you by the end of the day. And that is, most people see region A as being darker than region B. In fact, they have exactly the same intensity. If you go into Photoshop with this and you key around, you'll see they're the same. And this demonstration sort of demonstrates, so it blends perfectly in there, and then it blends perfectly in there, and obviously they're not perceived in the same way. So how do we explain that difference in apparent lightness? And this is the opposite of what you would predict from lateral inhibition. So lateral inhibition is not going to explain either of these phenomena. So just to summarize, we have the luminance ratio between two surface patches with the same illumination is a useful source of information for estimating their relative reflectance because the ratio is unaffected by the magnitude of illumination. However, this strategy is only valid if the surface patches to be compared have the same illumination. And illumination can vary greatly in different parts of a scene. That's the problem we're going to try to deal with. And so the idea, thus, it is necessary to have some sort of grouping mechanism that can isolate different parts of the scene that share the same illumination. So here's where the old Gestalt psychology that we talked about a while ago creeps into the picture. It's those grouping rules are going to play a big role in how we determine the color of a surface. And here's one of the most famous examples of this. How many of you have seen this before? All right, which is lighter, A or B? What do you think?
B.
B's lighter? Anybody disagree with that? Anybody think they look exactly the same? Well, let's see what they look like if I take this square and I move it in each one. So now it blends perfectly with B, and now it blends perfectly with A. You don't like these demos for some reason. Any ideas why this works?
It's something to do with the shadow.
What's that?
It's something to do with the shadow of the cylinder.
So what's the assumption of the ratio rule? You're going to compare the relative luminances of two objects under the assumption they both have the same illumination. But if you know that two regions don't have the same illumination, then all bets are off. You can't compare the ratios in order to judge which one is lightly. So what does the shadow tell you? Is this region getting as much light as that region? Why not? Well, because it's in shadow. The cylinder is blocking part of it off. And your brain is taking that into account. So if this region is getting less light than this region, but they're both producing the same luminance, this one must actually be brighter because it's getting less illumination. So all of this makes perfect sense. Now, one of the things that comes up when we have this discussion is this an illusion? Any ideas? What do you think?
Fooled me.
Well, it didn't fool you, because in fact, this region is lighter. This surface has less reflectance than that one. It's just they have the same amount of luminance. But lightness is perceived reflectance. It's not perceived luminance. And your judgments about reflectance in this case are right on. This region reflects more of the incoming light than that region does. So yeah.
Okay, so I'm kind of very confused now. Since B clearly looks lighter than A, you're saying that because there's a shadow there, our brain is saying that it is lighter, it appears lighter.
No, what the brain is saying is that A is getting more illumination than B is.
Okay.
Both surfaces are giving you the same luminance. So what is lightness? Lightness is luminance divided by reflectance. Is illumination divided by reflectance. So if they're receiving different illuminations, and your brain takes that into account, then this one ought to appear like it has a higher reflectance than that one does. And that's in fact what's really going on here. It's not an illusion. You're seeing what's actually there. Any other questions about this? Yeah.
Okay, so your brain thinks that it has less reflectance, but it actually has more reflectance. Is that what you said?
No, I'm saying the brain, this actually has more reflectance than that does. That's why this looks white and that looks black. The difference is the illumination. Right? What's reflectance? Reflectance is the proportion of light that is reflecting off a surface. So let's just say hypothetically that A is reflecting 10% of the light and B is reflecting 20% of the light. And because of the shadow, A is getting twice as much light as B is. So what's reflectance? You have that 10% multiplied by the, well, let's put it in real numbers. So let's say A has 20 units of light and B has 10 units of light. So what is the luminance going to be of A? Well, it's reflecting 10%, and you multiply that by the luminance of 20. So it's like 2 units of light are reflecting off. This one is reflecting 20%, but it's only getting 10 units of light. And so you get the same result in luminance. The luminance is the same. Is this clear, hopefully?
So if we get rid of the little cylinder, if we get rid of the cylinder and all that stuff, how would it look then? Would you be like totally different? Or no?
Yeah, it would look, well, no, it would look exactly the same. It's just that you wouldn't have the shadow here, and if you measured, this would still look black, that would still look white, but they wouldn't have the same luminance in that case. A would have more luminance than B would.
So the square thing would, you couldn't take that little rectangle, put it over B, and then put it over A.
Yeah, it wouldn't work in that case if you took away the shadow. Yeah.
Is illuminance and luminance the same thing?
No, illuminance is the same as illumination. Luminance is, so illumination is the light that falls on the surface, and luminance is the amount that reflects off a surface. Yeah?
Which of those qualities is what your brain is comparing? Is it luminance? Is it reflectance? Which one is it?
Okay, lightness is all about reflectance.
Okay.
So how much is the surface reflecting? That's what makes a white surface look different from a black surface. Black surface reflects about 10% of the light. White surface reflects about 90% of the light. 85 or 90. The problem is illumination varies a lot. So you can have a white surface with the same luminance as a black surface if the black surface has high illumination and the white surface has low illumination. And that's what's being played on here. So, and I'm using language I don't like. The brain takes the light into, the shadow into account. I mean, I don't think that's what's going on. I'll show you more clearly a little later. But the shadow is clearly having an effect on how you're interpreting this scene. And you're interpreting it correctly because this is indeed white and that is indeed black. So when you go in and you measure this in Photoshop, you're looking at the image properties. That's misleading. What you're interested in is how our perception is mapping onto the real world. In this case, it's mapping on correctly. Any other questions before I move on? So here's another example of this I pulled off the web. I think there's something funky about this. I'm not sure it's what it seems to be. I suspect that may not be a real shadow. It's just painted on there. But I'm not 100% sure of why this works. Just to show you doing a similar demo to what I showed you, only this type in real life. All right, now yeah.
Yeah, so that's like very similar to yesterday or the other day. You're talking about really bright light shining onto a black surface, right? And then you take a piece of paper and you put it next to it.
Exactly.
Same thing. And then,
Exactly. So you're looking at the relationships among the different surfaces. If you strip that away, then you're going to get fooled. But if you have enough, and there's a fancy word that people who study lightness they call it articulation. It's the more different reflectances you have in the environment that you're able to see, the better able you're able to make sense of them. If you want to fool people, you just want a few reflectances. That's the optimal way of doing that. Now, one of the papers I assigned you is by a guy at MIT, Ted Adelson, who's one of the leading researchers in this type of research. I think I've mentioned him several times so far in this class. And the next few slides are from him. And basically, a really nice way of thinking about it is that when you're looking at an image, you have part of the differences that you see are due to illumination, and part of the differences you see are due to reflectance. And so the question is, how do you tease those things apart? That's the theme of this whole set of 3 lectures. How do you tease apart the illumination from the reflectance? And the way that he does that is, suppose you have this brick here that you see up here. So here you have variations in reflectance. These are darker than those, but you also have variations in illumination. So you got more light coming from the top than you do from this side, and this has a little more light than that side. And so one way to partition this space is you say, all right, I'll consider an image that just has the reflectances and none of the variations in the illumination. We'll call that the reflectance image. And then I can consider where all of the changes that you see are due to the illumination and none due to the reflectance. So this is called the illumination image. And what Adelson is now going to propose is some grouping schemes to help us separate that. So what he's going to look for are regions that are likely to have the same illumination. And they're going to be critical in order to determine the perception of lightness. So let's see how that works. So let's consider this up here and this down here. Now, you remember the last question on the test last time. What was the last question on the test? Anybody remember the last question on the test? Yes.
About the contour, different contours.
Yeah, what are the different kinds of contours? I thought it would be the easiest question on the test, but it turned out not to be so, because a lot of you just listed the contours but didn't describe them. This is an example where knowing what the contours are can really help you in terms of figuring out different lightnesses. So what kind of contour is circled on the top up here? Convex corner. And what kind of contour is circled on the bottom? It's a reflectance contour. You almost all got this on the test. You forgot it that quickly. So this is due to a difference in reflectance, and the one up in the corner is due to a difference in illumination. However, if you just look at the patch in isolation, the difference in color across that edge is exactly the same. So in order to understand what's going on, it's really important to understand the nature of the contour that's separating this region from that region. And let's talk about how to do that. And so what I'm going to do is I'm going to introduce to you, this is one of the earliest things that people did in computer vision, was to try and label contours. I think the first AI vision program was done in the 60s by a guy with the weird name of Adolfo Gutzman. And his PhD project was to take line drawings like that and to label what the contours were. And the way that he did it was to exploit different kinds of vertices. So you see this vertex structure like here? See how it's shaped as a Y? This is called a Y vertex. See this one here? It's shaped like the Greek letter psi. It's called a psi vertex. This one here is a T vertex. This one here is an X vertex, and this one is called an L vertex. All right, so these are different kinds of vertices, and they provide important information, which we've known about for a long, long time, about the underlying contour that's being separated in the different regions. So here are some of the rules. If you have a T vertex, like right here, the argument that any luminance difference between these is probably due to reflectance. Why is that? Well, because these are have the same orientation relative to the light source. But you can't pay any attention to the relation between what's going on in these regions and what's going on over here. What the crossbar, the T, is saying, the two things below the contour, the crossbar, are related, but the stuff above the contour is the background. Psi vertices are very important. And so you have the baseline of the psi and the two flanking lines. And so what the psi says that B and D have the same orientation, therefore the same illumination. C and E have the same orientation and the same illumination. But you can't say anything about D and E or B and C. Arrow vertices tell you that D and E are different orientations, therefore they're getting different illuminations. All right, everybody clear on this? So the idea, here's the idea from grouping. What the idea is that when I find things that have the same orientation, that means they're likely getting the same illumination, and any differences in luminance between those regions are probably due to reflectance. If I have two regions that are at different orientations, it's likely to be the case that any differences in luminance between those regions are due to differences in illumination. All right, so the lightness is we're trying to spot differences in reflectance. So let's see this at work. Remember our friend the White's illusion. What kind of vertices do you see here?
Psi.
We'll go back. These are the vertices. So where's a psi?
Doesn't it say T vertex at the top?
Yeah, it does say T vertex at the top. That's a good guess. This is one of our graduate students. The T vertex at the top. And what does the T vertex tell us? That the two things below the crossbar are at the same orientation. And therefore, any difference between those things is due to reflectance. Stuff on the other side of the crossbar doesn't mean anything. What's going on here? All right, so what's on the same side of the crossbar? We have B, which is gray, which is now being related to black. Which of those two is lighter, B or the black? And over here, I have A, which is gray, is related to the white. Which is lighter in this comparison? So if you say within a group, if the lightest thing is light and the darkest thing is dark, then this should be lighter than that. That's the grouping explanation of the White's illusion. And the key thing to keep in mind is that lateral inhibition predicts exactly the opposite. So this is a pretty strong test that grouping is important. Let's take this example. Now I'll pick on you again. So what kind of vertex do we have here that's labeled over on the left?
Psi, yeah.
It's a psi. And what does the psi vertex tell us?
That differ from illumination because of the difference in reflectance.
So A and B, based on the psi vertex, have the same orientation. Therefore, they're getting the same illumination. Therefore, the difference in luminance you see can be attributed to reflectance. You all get the gist of that? But now let's change it a little bit. And I'll take that blue panel and I'll move it over there. And you've got another psi vertex right there. What's it telling you now? Do A and B have the same orientation or different orientations?
Different.
And so you attribute the lightness, the difference in luminance there to illumination. A and B look like they have the same lightness. But it's the same A and B. So if we go back and forth, here they're different reflectance, different lightness. Here you're attributing that to difference in illumination. Now, of course, the reason this works is this is an impossible figure, but you can't tell that with the blue square there. Here's another example. Let's take, which of these two regions appears lighter? The bottom one or the bottom one or the top one? Now, what is the psi vertex telling you? Do those two regions have the same orientation? Which means that they get the same illumination, which means that the difference in luminance that you see there is due to reflectance. Now, this is an interesting example because these also have the same orientation in 3D, but there's no single vertex that's telling you that. And so the psi can't explain what's going on in this case. So in this case, the psi vertices indicate the two patches of the same coplanar group, and they're perceived to have the same shade of gray. In this case, the two designated region patches are in different groups, even though they're the same orientation, and now you see them as very different lightness. So the key here, when I've been telling you the brain sees these things at the same orientation, I was misrepresenting things. It's not that the brain is necessarily pulling out the 3D orientation, it's just taking regions and grouping them together. So if regions are in the same group, you're going to attribute differences to reflectance. If they're in different groups, you'll attribute them to illumination. So note how the object on the left appears composed of two blocks. Object on the right is composed of two cylinders. Does the shading look the same on the left as it does on the right? If I take away that part, those two regions are exactly identical. So a lot of this is being governed by the contour structure in the image. So here's another example. A lot of these came, by the way, from, there's a big meeting called, there's a big society called the Society of Vision Science, and they have a meeting every year at some nice place in Florida. And one night during this meeting, they have what's called Illusion Night. And for a number of years, the people who do lightness research would come down and present their best lightness effects at this meeting. So a lot of the slides I'm showing you are contestants in the best illusion contest. And the next few I'm going to show you are really good lightness effects. And they also reinforce the point that it's grouping that matters and not your perception of three-dimensional structure. So let's look at this case. This probably doesn't look like a 3D thing at all. It's just a flat pattern like a plaid. And if you take this region here and this region here, which one looks lighter? The one on the left or the one on the right? How many of you say the one on the left? Raise your hand. Boy, I really got you shell-shocked now, because... All right, so it's this region and that region. Do you all agree the one on the left is lighter? Yeah. And they're not even close, are they? I mean, this is much lighter than that is. Do you all agree to that? All right, well, let's do our little test. Oh, before we do that, where are the psi vertices here?
Where the red arrows are pointing.
All right, so you got a psi vertex right here, a lot of them right here. So this is the base of the psi, this is the flanking regions. And what the psi vertex is telling you is all this stuff is related to each other, but it's not related to the stuff here. And all this stuff is related to each other, but not related to the stuff over there. So the grouping is telling you that this whole region is a group and this whole region is a different group. So let's see how that affects your lightness. So we have a little square there, and it's going to move along, and it fits right in there. Now we'll move it over here. Fits perfectly again. You think I'm playing games in Photoshop here. I'm actually you can see the color change as it crosses the boundary. That's what's cool about this demo. We'll move it over to here. It fits again. Move it over here. And fits again. Now in this case, there's no perception of 3D structure. It's solely due to the grouping by the psi vertices. Now let's move on to another kind of thing that's related to the Kafka demo I showed you a bit earlier where it looked transparent. Let's take the pattern to the left. How many of you see a transparent layer? And which one looks on top, the darker one or the lighter one? How many of you think the darker one looks on top? Raise your hand. How many of you think the lighter one looks on top? Raise your hand. That's about 50-50. In this particular case, it is completely ambiguous of who's on top. Let's consider the second one in the middle. How many of you see transparency here? Raise your hand. How many of you see the darker one on top? Nobody. How many of you see the lighter one on top? Everybody. All right, so the thing that's driving this is what's called an X. Oh, and how about here? Does anybody see transparency here? Raise your hand. So what's driving this are Xjunctions. It's these things right here. And it turns out that the Xjunctions can have multiple interpretations depending on how the pattern of light around them is changing. So let's look at this one. So what we're going to do is we're going to connect the darkest one to the next darkest one to the next darkest one to the lightest one. And if you do that over on the left, you get an N pattern or a Z pattern. If you do it to the one in the middle, you get a U pattern. And if you do it to the one on the right, you get an X pattern. So the rule is, if you have an X junction and the ordering of luminances is an N or a Z, then it has two transparent interpretations. If you have an X junction and the ordering of luminances is a U, then it has only a single transparent interpretation. And if you have the order of luminances is an X, that means you have no transparent interpretations. So let's see how this works. How many of you see a haze in the left pattern that you don't see in the right pattern? Raise your hand. All right, this is coming about because of transparency. That haze is you're seeing that as a transparent layer. Now this is a wonderful demo, also by Ted Adelson, made a movie about this. So on the left side, you have a type 1 X vertex. On the right side, you have a type 2 X vertex. So here's the pattern before any vertices are applied. And now what we'll do is we'll add some additional structure. And now you see the haze on the left. Now here's the cool thing. All I'm going to do is rotate those little disks. Well, I'm not going to do it. Whoever animated this was some student of Ted Adelson's. And now you see the haze on the right. All right, so what he's doing there, he's changing where the type 1 and type 2 X vertices are. And if we take it away altogether, you don't see any transparency. So this is vertices at work, trying to help you interpret what's going on in these scenes. How do I stop this thing? One of the things I hate about Flash is you have to be outside the animation to, it's just not working. All right, I'm gonna have to get out of here altogether. All right, let's see another illusion that plays on this. Here we have which region looks brighter. Well, let me back off. Do all those four squares look like they have the same shade of gray? Raise your hand if they look the same. All right, well now let's move them into different contexts. Now do they look like the same shade of gray? Let's move them back and let's move them in. They don't even look close. Again, this is being driven by the X vertices that are telling you there's a transparent layer. Now, if we change this a little bit subtly to this, now if I move them in, there's hardly any effect. So let's back up. With the X vertices, they define the groupings, and you get this huge color difference for things that otherwise would have the same luminance. However, if you get rid of the X vertices, but you have the same basic pattern, now you move the stuff in, and hardly any effect at all. So lightness is a cool phenomenon, and it's very much affected by grouping principles. All right, let's move on to something a little bit more sophisticated. So what we have been talking about so far is how can I tell if something is white versus something is black? But when you have shiny surfaces, that changes things a good bit. So where are take the object on the left, that sort of hokey looking torus object. Is this band darker than that band?
Yes.
But which one has the highest luminance, this or that? Right? This is the highest luminance. This is brighter than anything over here. And what is this structure in an image? Again, think back to question number 6 that almost all of you answered.
A specular highlight.
A specular highlight. Excellent. Specular highlights have absolutely nothing to do with the color of the surface. They have nothing to do with the proportion of reflectance. They're reflections of the light source. So the fact that this is really bright isn't telling you that this is the light thing and that's the dark thing. What it's telling you is that this ring is shiny and that ring is matte. And that's the next question that we want to worry about, is how do we tell the difference between not just light things and dark things, but shiny things versus not shiny things. Not shiny things are called matte. And so this is an experiment I did a number of years ago. Actually, we did it back in the early 90s. But my coworker, Ennio Mengola, had pissed me off for various reasons I won't go into. And so I swore that I was not going to write this paper. And so I waited 13 years for him to write it. And so finally, my other co-author, Farley Norman, was going up for full professor. And he said, Jim, can we please do this paper? So I could be a hard ass on Mengola, but Farley would take the shirt off his back for me, so I couldn't turn him down. So we wrote the paper, and it turns out it was much more relevant in 2004 than it would have been in 2001. So it was probably a good thing that we waited 13 years. But anyway, what we showed is that people are able to discount specular highlights. Specular highlights have almost no effect on the appearance of lightness. Now, there have been a number of papers on the perception of gloss. This is a famous one by Motoyoshi, Nishida, Sharon, and Adelson. You see Ted Adelson's name a lot in this kind of work. And what they did is a statistical analysis where, how many of you have used Photoshop before? So a good chunk of you. So when you have an image in Photoshop, one of the things you can pull up is a window that is a histogram. And what it does is it just plots all of the pixels that have a particular intensity. And so what Motoyoshi et al., they had a science paper that showed this, that if you have a skewed histogram where the skew's in the positive direction, that this is characteristic of shiny surfaces, where if you have skew in the other direction, that's characteristic of matte surfaces. Now, almost immediately when this paper came out, there are a lot of researchers in the field that said, wait, this is total nonsense. We know that's not the case. And we've known it for a long time. But this got into science anyway. And science doesn't let you write rebuttals. They just do the original paper, and that's that. But here's some examples from a reply paper by Bart Anderson, who's one of the leading researchers in this field. So here we have an example of the one on the left here, A, where you have a really skewed positive distribution, but it doesn't look shiny at all. And here's one where you have, again, a really skewed positive distribution on the right, and it also doesn't look shiny. So the skewed distribution per se isn't going to do it for you. Here's a demonstration from that same paper, Todd Norman and Mangola, where what we showed is that in order to see something as a highlight, it has to be oriented in just the right way relative to the surface curvature. So in this particular case, does the surface on the left, does it look shiny to you? How about the one on the right? So what we did in this case is that we just took the highlights there and we just rotated them in place in the image. So the one on the left is a composite. We rendered the matte part and the shiny part separately. And then when you composite them, you could rotate the shiny part and leave the matte part in place. And you get this thing over here. And now those don't look like highlights. They look like a swash of paint or stray light or something like that. So the key thing here is that highlights have to be oriented with the surface curvature. The first guy to discover this, there's a paper by Beck and Prosny, I think in the early 70s. So we weren't the first to show this. I was just making this image to copy what they did. I don't know how they did what they did because it was before computer graphics was around, but anyway, they did it. Now, that leads us to another topic that I want to talk about, which is color constancy. I probably should have switched these around. Why did I do it this way? Oh, I did it this way because highlights get discounted. It's not just the luminance that's matter. You have to identify the highlights as well, and they don't count in the lightness contributions. But now let's talk about color constancy. So that's another problem we have to worry about. How do you tell the color of an object from the color of the illumination? So here's an example. This is the graph on the left shows a tungsten light bulb. They pretty much don't exist anymore. They may be coming back because of Trump. I don't know why, but and we have sunlight, and they have different distributions of wavelength. So if you look at an image done in daylight versus in tungsten, see the tungsten has a more reddish color to it. But we don't experience that in the real world. If you were in these same scenes, you would perceive the colors correctly. And so one of the big questions is, how is it that you're able to do this? And the way you're able to do it is you take into account the colors, so you somehow can make an estimate of what the color of the light is and take that into account. So what color is this square here? And what color is this square? If I told you they were the same, Would you believe me?
No.
Haven't you learned yet? This is a demonstration by Dale Purvis at Duke University. And so what I'm going to do is I'm going to take away all the context and just show you those patches in isolation. They all look the same gray? Now you have ones look yellow and one look blue. So what are you doing here? In this case, so those yellow guys are all actually gray, but the visual information is telling you that the illumination is blue. So if you're getting blue illumination and the reflectance is gray, what does that mean? That the surface color must be yellow. And similarly, if you're getting the illumination is yellow and the patches look blue, I'm sorry, the patches are actually giving you a gray reflectance, that means the patches must be blue. So your brain is taking into account the color of the illumination which you're getting from this contextual information. Yes?
So it only works when the colors correspond to the, like when there's another color that corresponds to the light, the illuminance?
Well, if the light is, I mean, it changes all the, you don't see any of the colors the same way as you would if you didn't have information that the light was yellow. So if you have the light is yellow, you take that into account in judging the reflectances of everything else. So the key of this demonstration is you're getting really salient information on the left that the light really is yellow, and you're getting really salient information on the right where the light really is blue. Now, does anybody have an idea where I might be heading with this? What's that?
The dress.
Oh, I have to get out of this again. What a good guess. So how many of you see blue here? How many of you see white? Let's do a trick. Let's put the dress, this was insight, this demo, do you all remember the day the dress came out? And it was just over email, what was this, about 3 years ago? 4 years ago, something like that. I woke up that morning, I had 50 emails from ex-students asking me what the hell's going on here. And my response was, well, it's probably something to do with color constancy. But there was a woman at or a young graduate student at MIT who came up with the idea of, well, it's got to be color constancy. And so what she did is she took advantage of Dale Purvis's demonstration, and she said, all right, let's put the dress in these two scenes. What do you think you get? All right, so here's the dress. And now we put it in the yellow one. All you white, are you a white dress person? Does it look white in the yellow one?
It looks like grayish.
But it doesn't look white.
Not
Can't see it blue?
Doesn't look blue either. It just looks like dark white, like a gray.
How about the blue people? Do you see it as white over here?
Yes, please.
All right. So this is Rosalasa Sus, that's her, where she pasted her, this is a brave woman, right? She put her head on that hideous dress. But it doesn't look too bad on her. In any event, what she showed is that the reason we see it differently is different people make different default assumptions about what the illumination is. So if you assume default that the natural way of lighting things is blue, which is not crazy because the sky's blue, right? Then you should see white on gold. If your default assumption is that the light is white or yellow, because that's the color of the sun, then you see blue on black. So, interesting study. Again, she came up with this literally the day after that image trended. And I've seen that next year at that Vision Science Society meeting I told you about, there were 2 whole sessions devoted to this dress. I think I told you this last time, that when I was in Belgium earlier this semester, I was with a woman who was one of the leading color researchers in the world. And she told me that she bought every version of this. Apparently there are about 5 versions of the dress in different colors. And the only thing that everybody agrees on is that it's a hideous dress. But
Can you do it in other colors other than yellow and blue? Like what if you did like red and green?
probably not,
Okay.
because assuming a default blue assumption is reasonable,
Yeah.
because the sky's blue, a default yellow assumption or white assumption is reasonable, because clouds are white and the sun is yellow. Red, not so much. Green, not so much. So, you're not going to have a default assumption that's going to push you around in those domains where you would in the blue-yellow domain. But, yeah.
Okay, so in that dress where you have the little, patches that have been taken from both the images, is that what it's supposed to look like all the time then? Or is it because of the white background? Is that?
So the top is so you've stuck it in information where there's a lot of information about the light source, so you'll override the brain's default. The ones on the bottom are where you pulled it out. So literally, I did this in Photoshop. I took a rectangle out of here and I took a rectangle out of there and I put them together just to show you they're the same thing. But they look really different when you see it in context.
Right, but I'm guessing like in the original picture, like if you see them to be the way that you like pulled them out there, that like that weird like almost off-white, and it's not like a gold, but it's like a brownish, like if that's the perception maybe give of it, like that it's neither white or blue. then
Well, let's go back.
Like when I look at that, I don't see either blue or white. Like I see like a dirty, like you washed your dress with some jeans.
Yeah, I see this as blue and dark brown.
Okay.
Now you got to keep in mind that the colors are changed by the projector. The colors are changed by when these were put into Photoshop. The colors get contaminated all the time, so these aren't the pure colors. Yeah.
If we were to see this dress in person, in the same lighting, would we all see the same color?
Oh, what a great question. I don't know the answer to that. I suspect you would see it correctly.
Right, so I wonder what the
Which is,
actual
by the way,
color-
blue and black is what the dress really is.
Oh, is it?
And the reason for that is you've got a lot of contextual information that's telling you about the illumination.
Right.
That's the thing that's driving it. Now, so I'm betting, I don't know this for sure, but I'm betting somebody took this picture, had no idea they were taking something that's unusual, and it just, when people looked at it after the fact, that they disagreed about what they were seeing. Like, wait a second, that's not the dress that Agnes was wearing. And the other person said, well, yes, it is. And then you get in a fight and somebody posted it on the web, and next thing you know, I'm getting hundreds of emails. Even though I'm not an expert in color. But I've had hundreds of students take this course and my other perception course, undergraduate one. All right, let's switch gears a little bit. I want to talk now about our perception of surface materials. So here we have a number of different, say, take the one on the upper right. What does that look like? Anybody want to venture a guess what that material is? I'm sorry?
Rubber?
Rubber? That's not a bad guess. How about black velvet?
I was gonna say clay.
You were going to say what? Clay? Well, clay wouldn't be shiny like that.
The upper left.
Oh, the upper left?
How do you say it? Or-
Oh, yeah, that would be perfect clay in the upper left. How about the upper right? How about the one in the middle of the upper row?
Like aluminum.
How about the one in the middle on the middle row?
Steel.
How about the one in the middle on the bottom row?
Like plastic or glass.
How about the one on the left in the bottom row?
Or
Anybody see wax in that one?
That looks like a gummy bear.
I'm sorry?
A gummy bear. Yeah, yeah.
So the idea here is we can look at these different materials, and during the last, I don't know, 6-7 years, there's been a lot of research on how we do this. So classically, when people look at this, it's been a study of lightness. Lightness research has been going on for 100 years. Looking at more complex materials is a much newer line of research. So let me tell you a little bit how that works. So this is a repeat of a slide we did last time. The one on the left is polished metal. Actually, that's polished chrome. The one on the right is a matte surface, and the difference between them is because of the surface microstructure. So if you look at with an electron microscope on the one on the left, the surface is really smooth. Whereas if you do the same thing for the one on the right, the surface is really rough. Now, one of the things that got me interested in this is I've been doing computer graphics since the 1970s. And when the raster graphic stuff came out, I started playing around trying to do metal, and I couldn't get metal to look right. It was driving me crazy. And I just couldn't do it. And so one time, one of my graduate students was doing his PhD defense, and his father came to the defense to see it and go to the party afterwards. And his father happened to be a photographer. And so I asked him a question about how the hell do you shoot metal? And what he told me was, same thing for glass. How do you shoot glass? And he said it's critical to get control of the light field. So any of you gone to a professional photographer before? If you look at them, they have these lights that they can move around and those umbrellas that diffuse the light. So they spend a lot of time adjusting the lights before they take the shot. And they're pros, so they know what they're doing in setting up the light to do different materials. In fact, if you get on the web, you see long blogs about how to do lighting to photograph different kinds of material. And so the insight he gave me, so I got on the web, and it said the way to do metal is you want light coming from a lot of different directions. And so what they do is they get a translucent box, and they illuminate it from outside the box. So the light hits the box, goes through it, gets diffused, and then it's in all directions, and you get really good looking metal that way. So in order to study that, what I did is we looked at 3 different kinds of lighting. One where you have one of these translucent boxes where the light goes through the walls and illuminates the object that way. We had 2 square area lights and then just a single point. And this is what you get. So if you use the diffuse light with the box, you get great looking metal. That's the left column. Do you all see metal in the left column? How about the middle column? Do you see metal there? How would you describe the middle column or the right column? What's that look like to you?
Plastic.
I'm sorry?
Plastic.
Black plastic? How many of you see black plastic in the middle and right columns? All of those are the same metal material. The only thing that's differed is the pattern of light. This is why I was having so much trouble simulating metal surface. I was using the wrong kind of lighting. And so once I discovered it, I said, shit, I can get 10 papers out of this. I'm up to 5 now, so it's... And this would be an example of a shiny white material. So it's shiny, but it doesn't look white. Yeah?
So a software that they teach all of us freshman engineers is SolidWorks, where you build computer-aided design things and you can change materials and move them around, and it looks real the whole time. Do they use this, or do they use a different?
I don't know the particular. I've not used SolidWorks myself. There are a number of different ways of doing metal. You can definitely do either of these in SolidWorks. How skilled at it are you?
Yeah, good enough.
I'd have to know what the parameters are when you're specifying the material. And if I knew what the parameters were, I could tell you exactly what it's doing.
It's a single material parameters. You say, I want this one object out of steel, or stainless steel, or iron.
Oh, okay. If that's the case, then it's doing exactly the same thing the renderer is doing here. This is chrome. I'm not sure we can perceptually distinguish between steel and chrome, by the way. What we see is metal. I'm going to have to quit now so I can pass back the exam, but this will be a setup for what we'll do next time, and we'll go into more detail about that. I'll give you the underlying physics about how it is that different materials are distinguished from one another. There are basically 2 things going on. One is how much of the light gets reflected. So for something like shiny black, it's only reflecting about 5% of the light, whereas something like silver is reflecting almost 100%. And the other thing is how the reflectance changes with the incidence angle. And I'll go into more detail about that later. But let me stop here and pass out the exams.